Alright, I'm going to start off reading the problem statement. We have an unequal T connection in a plumbing circuit, has a 10 centimeter diameter inlet, a 4 centimeter diameter outlet, and a 7 centimeter diameter outlet. It says we have water at 400 megapascal and 25 Celsius, enters with a velocity of 10 meters per second, and leaves the larger outlet with a velocity of 5 meters per second. So it wants us to assume that the pressure and temperature of the water at the outlets is the same as the inlet. And then the question asks, what are the mass flow rates at each of the inlet and outlets? Also, it wants to know what is the velocity of the water at the smaller outlet. So with this problem, this is kind of our first problem that we've been working in Chapter 4. I'm going to walk you through the steps, and we'll start off with defining the system. So whenever we're defining the system, we still just stick with the same kind of general process that we've done before. We have water as our substance, that is the system. And then we specify what type of device we have. In this case, we have water in a T connector. So we have water in a T connection, that's our system, and then we go ahead and still classify the system according to, we classify water as a phase changer. And the T connection here is an open system. We have mass flow in and mass flow out, so now we're dealing with an open system. For the sketch, all of the sketches that we're going to be doing in Chapter 4, we just want to kind of do an engineering sketch. I'm not going to require a properties sketch for any of the problems in Chapter 4. It's simply enough to just go ahead and give me an engineering sketch of what the system is. So for this case, we have a system with one inlet and two exits. So this is our T connection here, and we have one inlet. We're going to go ahead and give these arbitrary names. It is arbitrary. We're going to call this one inlet number 1, and then we'll call these as exit number 2 and exit number 3. So always in Chapter 4 in the open systems, we name our, instead of naming the states, like at the beginning of the process we used to call it state 1, and at the end of the process we call that state 2. Instead, in Chapter 4, we're always going to name our inlets things like 1 and our outlets things like 2. And then if we have multiple inlet, multiple outlet like this scenario, then we can give them 1, 2, 3, just kind of arbitrarily. So this is kind of the engineering sketch, and then we'll go ahead and continue on to the conditions next. So the conditions, just like it was in Chapter 3, the conditions can be chapter specific and they can also be problem specific. So the chapter specific condition in Chapter 3 was that we were talking about closed systems. So that meant that we had a constant mass. In Chapter 4, there's one chapter specific condition that all of the problems share in common, and that's that we're studying steady flow device. So we're going to go ahead and put in the chapter specific condition, which is we have a steady flow device, and we've already talked about what it means to have a steady flow. That just means that we use the steady flow form of the mass balance and energy balance equation. And then any other conditions are basically problem-specific conditions. This problem gives us one main problem-specific condition. It says assume that the pressure and temperature of the water at the outlets is the same as the inlet. So we can kind of just write that down, pressure and temperature. We can also, instead of that, we can just say that whatever P2 is and whatever P3 is, it's the same as the inlet pressure, P1. And then also whatever T3 and T2 are, that's the same as the inlet temperature, T1. So what is this really telling us? What type of ramification does this have? Right? Steady flow means that we use the steady flow form of the mass balance. But what about constant pressure and constant temperature? Or actually not constant, it means same pressure at the exits as at the inlet. Alright, what that really means for us is that we have what's called incompressible flow. We have incompressible flow. So if the properties at the inlet are the same as all the exits, then typically we're going to have what's called incompressible flow. Incompressible flow is basically whenever you have a liquid throughout the entire system. So right now we don't know that we have a liquid, but we'll be able to see once we check the inlet conditions that we actually have a liquid. So we don't have to put incompressible flow here right now. We can put that in there later. So for right now we can just say that exit pressure and temperature is the same as the inlet. Next we have all of the properties. So for the properties we are given information about the diameter of the inlet, and the inlet we call number 1. So we're going to write down that the diameter of the inlet is 10 centimeters. If we want to, we can go ahead and convert that to meters, because meters is our standard unit. So I'll go ahead and convert it into meters. Then we're told that there is also 2 outlets. We have the 4 centimeter diameter outlet and the 7 centimeter diameter outlet. So we're going to just arbitrarily name those 2 outlets 2 and 3. So here we'll mark that the 10 centimeter diameter inlet, that's referring to inlet number 1. The 4 centimeter diameter outlet, that is referring to everything that we're going to call 2. So that's outlet number 2. It has the 4 centimeter diameter outlet. And then the 7 centimeter diameter outlet, we're going to be labeling that as outlet number 3. So we'll go ahead and mark down those diameters as well. The diameter of outlet number 2 is 0.04 meters, or 4 centimeters. And then the diameter of outlet number 3 is 0.07 meters, or 7 centimeters. Next thing we read in the problem statement is that we have water is our substance at 400 megapascal and 25 degrees Celsius. And then those are the properties as the water enters the system. So we're going to say that P1 is 400 megapascal and T1 is equal to 25 degrees Celsius. So those are inlet conditions. And then it also says that the inlet velocity of the water is 10 meters per second. So we'll mark down the inlet velocity V1 is equal to 10 meters per second. Next it says that the water leaves the larger outlet with a velocity of 5 meters per second. So the larger outlet would be the one that has the 7 centimeter diameter, and we're told that the velocity of that outlet, number 3, is 5 meters per second. And then last, we're said assume the pressure and temperature of the water at the outlets is the same as the inlet. We already listed that in the conditions, so we don't necessarily need to list that again. Alright, so now the problem is set up and ready to go ahead and start solving. So what is the question asking us to solve for? It says what are the mass flow rates at each of the inlets and outlets. So we're looking for mass flow rate at the inlet 1, mass flow rate at the inlet 2, and mass flow rate at the inlet 3. What are those values? Also, it's asking us to find what is the velocity of the water at the smaller outlet. That would be outlet number 2. So we also want to know what is the velocity at outlet number 2. So we're solving for 4 things: mass flow rates at each of the inlets, outlets, and the velocity at outlet number 2. So what we have with the mass flow rate is we have an equation that tells us what the mass flow rate is. Our mass flow rate equation, we looked at this in the notes, is equal to velocity times area divided by specific volume. So what we can try to do at each one of the inlets, outlets, we can try to apply this equation to find the mass flow rate. So let's just look at inlet number 1. So at inlet number 1, if we write our equation, mass flow rate 1 is equal to V1 A1 divided by specific volume 1. So we're directly given information about the velocity of inlet number 1. It's 10 meters per second. We are given the diameter of the inlet number 1, so we can use that to calculate area. The only thing that we need to figure out for inlet number 1 based on properties is the specific volume. So looking at the properties at the inlet number 1, we know that pressure and temperature. So we have P1 is equal to 400 megapascal and T1 is equal to 25 degrees Celsius. So this is just a problem where we're looking up the specific volume of water based on the given pressure and the given temperature. So we use the same process that we've been using since the beginning of chapter 3. We have to first determine the phase of the water. So to do that, we can look up and compare our temperature T1 to the saturation temperature at P1. So here we can take a trip to our tables. So I'll pull up the table right here, go down to the pressure table and try to look up saturation temperature. So here's our saturated temperature table. Go down a couple pages and we get to the saturated water pressure table. So we're looking for 400 megapascal, which 0.1 megapascal is 1 bar. So 1 megapascal is 10 bar. And then we're going to be looking for 400 megapascal, so that should be 4,000 bar. So going down to the end of this table, alright, our table does not actually go to 4,000 bar. It only goes up to 220.9. So we're not actually going to be able to look up the saturation temperature at that pressure. So this isn't going to work. What we're going to have to do is try to use our other method of determining the phase. So we can also compare the pressure to the saturation pressure at the given temperature. So if we look up the saturation pressure at T1, going back into the table, now we got to go back up to the temperature table for water. Our T1 is 25 degrees Celsius. So at 25 degrees Celsius, we read off the saturation pressure is 3.17 kilopascal. And then obviously our pressure, 400 megapascal, is much higher than the saturation pressure at our given temperature. So in this case, if your pressure is higher than the saturation pressure, that means that we have a subcooled liquid. So the state at the inlet is a subcooled liquid. So once we have the subcooled liquid, we know that we can try to look up the specific volume in the tables. So we go to the tables. 400 megapascal is a very high pressure, so it actually has a chance of being in our tables. If we go to the table, we're going to scroll. Well, actually, I don't have the subcooled tables here. So what we can do is I'll open up the book and try to look at the properties in the book. So I'm trying to just thumb back through the end of the book until I get to table A5. That's the properties of compressed liquid water table. And then if I'm looking in table A5, I try to find pressure is equal to 400 megapascal or 4,000 bar, and the highest that I see in my book is actually pressure is equal to 300 bar or 30 megapascal. So even though we have a high pressure, it's still not in the compressed liquid water tables. So really our best choice, since we can't use the table value at all, is to just use our incompressible liquid approximation for the subcooled phase and just say that the specific volume 1 is approximately equal to V sub F at our given T1. So this is the incompressible liquid approximation. So really what we're doing, just need to look up V sub F at T1. So here was T1, it's 25 Celsius, V sub F 10029. And that's in meters cubed per kilogram. So that is our specific volume V sub 1. So based on those given properties, now we've found specific volume 1, we have velocity 1, and we can use the diameter to get area 1. Then we're good and we're set to calculate our mass flow rate. So the mass flow rate at the inlet 1 is equal to, we have V1 times our area. We just have to use the area equation for a circle. If we're given diameter, we can do pi over 4 times d squared, and then we're going to divide that by specific volume 1. So the first time we walk through this, I'll kind of work you through the units just to make sure that there's no strange unit conversions that show up here. So our velocity at the inlet was 10 meters per second. I'm going to put this on a new line. So we have 10 meters per second times pi over 4, that's unitless, and then multiplied by our diameter 1 squared. The diameter of the inlet was 0.1 meters, and then we need to square that. So far we have meters times meters squared, that's meters cubed per second. And then we divide that by our specific volume, where our specific volume was 0.001029 meters cubed per kilogram. So as far as the units go, here we have meters times meters squared, and then that's over meters cubed, so the meters all cancel each other out. On the bottom here we have seconds, and then this is in the denominator of the denominator, so it goes back up to the top. That means our units end up being kilograms per second, which is exactly what we want for the mass flow rate. So if you have velocity in meters per second, your area in meters squared, and your specific volume meters cubed per kilogram, no need to worry about any unit conversions for mass flow rate. So last thing we need to do is just punch this number into our calculator. So we have the mass flow rate 1 is equal to 10 times pi over 4, and then times 0.1 squared, and divide that by our specific volume, which is 0.001029. So mass flow rate at the inlet turns out to be 78.3 kilograms per second. So that answers the first question, mass flow rate at the inlet. Now what we want to do is go ahead and look at the outlet 2 and outlet 3, see if we can do the same thing, just solve for the mass flow rate. So looking at outlet number 2, if we write our equation, m dot 2 is equal to velocity times area and divided by specific volume. So we were not given information about the velocity, and we have no way to calculate velocity, alright, using properties analysis. So we're going to have to skip this part because we don't know mass flow rate and we don't know velocity at outlet number 2. We do know how to calculate the area of outlet 2 and specific volume. We can use properties to get but since we don't have this or this, we need to continue and try to do something else. So let's move on to outlet number 3. Hopefully we can solve for it. If we write our equation, m dot is equal to V times A divided by specific volume. So we have velocity, we can calculate area based on diameter, and we need to look up specific volume at the outlet number 3. So outlet number 3 has the same inlet pressure, same pressure as the inlet, and the same temperature at the inlet. So that means that it is also a subcooled liquid, and since it has the exact same pressure and temperature, that means that the state is exactly the same. Right? It has the same two intensive independent properties, so it's subcooled, and we don't even have to look up V3. We can just say V3 is equal to V1. It's also going to be similar for outlet number 2, right? V2 is going to be the same as V1 because of the same argument. P2 is equal to P1 and T2 is equal to T1. So just kind of a quick side note, we have specific volume is constant all the way through the device. So this is something that we mentioned just briefly. It's called incompressible flow. All that means is that we have a liquid flowing through the system the entire time, and the specific volume is constant. If we have incompressible flow, we also noted that there was an additional equation that we could use, right? And we're actually going to use that later to solve the problem as well. But for now, we don't really have to know that in order to solve this problem. Let's continue with solving for the mass flow rate at state 3, or outlet 3. So since V3 is known, specific volume 3 is the same as 1, we can go ahead and just plug it into this equation. Mass flow rate 3 is velocity 3 times the area, which is pi over 4 d3 squared. And then we have divided by specific volume 3. All of these numbers are known, and we already did the unit checks with mass flow rate 1, so no need to worry about the units here. We can just get that m dot 3 is equal to V3 is 5, and then we multiply times pi over 4, then times d3 squared, which is 0.07 squared, and divide by that same specific volume, 0.0010029. So mass flow rate at the outlet number 3 turns out to be 19.2. And then our units are mass per unit time, kilograms per second. Alright, so now the question is, what do we do about outlet number 2? We can't use the mass flow rate equation to calculate the mass flow rate because we don't have the velocity at exit 2. So we need either a way to calculate velocity at exit 2 using some properties analysis or something like that, or we have to do something else. We need some other equation. So think about it for a second and see if you can figure out what other information we have, or is there some other way that we can get velocity at the outlet 2. Alright, it turns out that there's no way that we can calculate velocity at outlet number 2 using the properties analysis because velocity is an extensive property. But we are missing some information that we haven't made use of in this problem. So we've made use of the mass flow rate equation, but we haven't made use of the conservation of mass equation. So we can also use the conservation of mass equation. or what we've also called the mass balance. So if we write the mass balance for this system, let's see what information that tells us. So the mass balance for this system, we need to use the multiple inlet, multiple outlet form, also the steady flow equation, which looks like sum of the mass flow in is equal to sum of the mass flow out. So we can just apply this equation to our T connection. We have one inlet, number 1, and then we have two outlets, number 2 and 3. So m dot 1 is known, m dot 3 is known. We can use this equation to now solve for m dot 2. So what we end up with is m dot 2 is just equal to m dot 1 minus m dot 3. So this is a simple addition problem. So m dot 2, we just take m1 minus m3. Sorry. This is equals. So m dot 2 turns out to be 59.1 kilograms per second. So now we've answered all the mass flow rate questions. We know the mass flow rate at each inlet and outlet. The only other thing that we needed to find was the velocity at the exit, number 2. So velocity at exit number 2, now we can use this equation that relates the mass flow rate for exit 2 to the velocity at exit 2. So here we can just resolve this equation for velocity 2 since we know m dot 2. So we get V2 is equal to m dot 2 times specific volume 2 divided by our area 2. We know specific volume 2 is the same as specific volume 1. We know mass flow rate 2, and we use our area equation to get area at exit 2. So we have here pi over 4 times d2 squared. So let's go ahead and enter that into our calculator. Again, we've already done this unit thing. We don't have to worry about the units here as long as we're using standard units. We'll get velocity 2 is equal to m dot 2 times specific volume 2, 0.001029, and then divided by, we have here pi over 4 times d2, which is 0.04 meters squared. So our velocity at outlet number 2 is 47.2 meters per second. Alright, this pretty much solves the problem. I also wanted you to see one additional way that you could have solved the problem once we realize that we have an incompressible flow like this. So that extra equation that we have for incompressible flow, instead of the mass flow rate balance, we can use a volumetric flow rate balance where we have summation in of the volumetric flow rate is equal to summation out of the volumetric flow rate. So we could have written this as V dot 1 is equal to V dot 2 plus V dot 3. And the volumetric flow rate is just equal to velocity times area. So this would be V1 A1 is equal to V2 A2 plus V3 A3. So we know velocity 1 and velocity 3, those are given in the problem statement. We know the diameter of inlet 1, 2, and 3, so we also know A1, A2, and A3. Then we could have solved this equation for velocity 2. So we could have also got velocity 2 is equal to A1 V1 minus A3 V3 divided by A2. And then if we put the area in terms of pi over 4 times d squared, this would look like A1 is pi over 4 times D1 squared, and then we have V1. We have minus A2, or sorry, A3 is pi over 4 D3 squared, and then we have V3. All of that divided by A2, which is pi over 4 D2 squared. So plugging all of this into the calculator, let's just check and make sure this gives us the same results. So V2 should be equal to, here we have pi over 4 times D1 squared is 0.1 squared times velocity 1. Velocity 1 is 10 meters per second. Then we have minus pi over 4 times D3 squared, which is 0.07 squared, times V3, and V3 was 5 meters per second. And we divide that by pi over 4 times D2 squared, which is 0.04 squared. So V2, get the exact same answer, is 47.2 meters per second this way as well. So this pretty much wraps up this equation, or this problem actually. We're using the mass flow rate equation, and we're also using the conservation of mass or mass balance equation to look at a multiple inlet, multiple outlet system.